Okay, and it's, so f is differentiable at x naught, and so this exists, and this derivative at x naught is a bijection actually. Okay, this fresh derivative is also a bijection. Then what will happen? That there exists a neighborhood u of x naught in, what do you call, x, and the neighborhood of v, so neighborhood of f of x naught, and a neighborhood, okay, v of, okay, of f of x naught in, say, y, okay, such that, and a map G, okay, such that this G can be treated, okay, so G is going to be a map from, say, V to U, such that this G can be treated as the inverse of F actually. Okay, this G can be treated as the inverse of F, you know, on what do you call, these neighborhoods actually. And this G is also differentiable. Okay, so you can also differentiate, what do you call, this G locally, you know, in V, for the points in V. So this is really, so I'm writing this, you know, local inversion theorem from my memory. Okay, so essentially it says you have a map between two Banach spaces and the points x naught and f of x naught. So if your f of x, f is differentiable at the point x naught and it's a bijection, then you are going to have, then there will be a neighborhood of u, then there exists a neighborhood u of x naught in x and a neighborhood of v of f of x naught in y, such that G and a map G from V to U, that G can be treated as the inverse of F in V. In other words, you can say that G composition F operated onto X, okay, is equal to X, okay, for all X in U, and F composition G operated onto some Y is also equal to Y for all Y in V. Okay, so this G is really the inverse of F locally, so it's a local inverse of what do you call F, and this G is also differentiable. Okay, so this G is also differentiable locally. So this is a rough statement of local inversion theorem. I can, you know, share a resource which is going to give you a precise description of the local inverse theorem as well actually. So, so I have wrote it from my memory, so maybe I have done, I have said something silly, but you know, the idea is correct actually. The idea is correct. So now, what we have? So I have a map N which is differentiable at origin 0, at a point 0, okay? And this map is also a bijection because it is equal to L. So the local inverse theorem will tell you, by local inversion theorem, there exists a neighborhood, okay, a neighborhood W1 of 0, okay, W1 of 0 of origin, okay, neighborhood W1 of 0 of origin in H, and a neighborhood W2 of 0 of origin in L2 and a map psi, capital psi. I'm going to use this by capital psi, not because the small psi is, I have reserved it for the equilibrium. So capital psi. So this is a map capital psi. That is a map from W2 of 0 into W1 of 0, and this map will play the role of the inverse of the map n actually, local, such that n, the calligraphic n operated onto psi of g is going to be equal to g for all g in W2 of 0, and psi of n of say g, okay, or v is going to be equal to v for all v in W1 of 0, okay? And also this psi map is also differentiable actually. We're going to use it as well. So we had map L, pi, calligraphic L, and now we have two important maps that are going to play the pivotal role in constructing the map on which we want to apply the Łojasiewicz-Simon inequality. Okay? So what is next? The next is that this map, now since if I, for example, call this u minus u cube a map G, a G of u, then G of u is a polynomial in U, so it must be an analytic map. And if this is analytic, okay, so this is analytic in U. Okay. Now, if this is analytic, then n, which is basically then L first of all, L, which is L plus the projection this and the map n, okay, which is m of m plus the map pi, okay, and the map psi. All of these are analytic actually, okay, all of these are analytic, okay, all of these are analytic. Why? Because L consists of this polynomial and what do you call the Laplace operator, which is analytic. So that L is analytic, so this capital L is analytic. N is also consists of what do you call Laplace u plus u minus u cube, so this is analytic. Pi is analytic, projections are always analytic. So if n is analytic, then its inverse is also analytic actually. So all these maps that you have, L, N, M, N, and psi, they all are analytic actually because they depend on this u minus u cube and the Laplace operator. Okay, so they are analytic. So since these are analytic, so the map N, M, okay, and psi, they all are analytic. Okay, analytic, and moreover, this n and psi, they are, Lipschitz actually. Moreover, there exists, say, the constant C, C1 or C2 such that, okay, psi of G1 minus psi of G2 is less than or equal to the constant G1 minus G2 for all G1 and G2 in W2 of 0, and the calligraphic N operated onto V1 minus the calligraphic N operated onto V2 can also be estimated. This is going to be H norm, and this is going to be, this is going to be the L2 norm, yes. And this is going to be the L2 norm, C of V1 minus V2 of H norm for all V1 and V2 in the neighborhood of what do you call it, W1 of 0. Okay. So what properties now we know about N and M and psi? So we know about N and psi in particular that they are analytic, they are differentiable locally, they are what do you call, Lipschitz actually. Okay, they are Lipschitz also. So these are some of the properties that we should know. And now, so in order to do this, let's first consider some exis. Exi is map exi to up to what do you call exi M. Okay, where M is really this M, the small m, is really the dimension of the kernel of the operator L actually. Okay, so this is the dimension of the kernel of the operator L. So I can consider exi M's, which are obviously elements in Rm, and if I wish, I can consider and choose these exis in such a way, or I can shrink them, or I can choose these components as small as like, so that they can satisfy, in other words, that when they are multiplied with phi I, the basis of the kernel of operator L, okay, this belongs to W2 of 0. Okay, this belongs to W2 of 0. So we can, so this is a general what we call in element in Rm, but if there will be need, and we will see basically that there is a need to define the map gamma, I can make them, these components, as small as possible so that this vector belongs to the what do you call, the domain of the map psi actually. Okay, the map psi, so that I can operate psi on this what do you call vector. And now let me define a map gamma from Rm into R, and from the domain, in the domain I am taking such vectors. Okay, so I am considering all such vectors for all such points for which this vector belongs to the W2 of 0, because I want to define the gamma using the map psi. So the gamma of the point xi is equal to E, which is the energy of the system, of psi operated onto the vector I equal to 1 to m, xi I and phi I. Okay. Now since this belongs to W2 of 0, I can operate psi on it, plus the equilibrium point psi. Okay, plus the equilibrium point psi actually. So this is a function, this is going to be a function in L2. This is also, you know, a function in L2. So this is a function in L2. So this is like U actually, and E is the energy, where E, let's say that, where E is energy of problem star. And if you remember the expression for E, the E of U is actually the integral with respect to the space variable of gamma Laplace U square upon 2, delta U square upon 2, plus U power 4 divided by 4 minus u square upon 2 dx. Okay, so this is really the definition of E of u. And this is my definition of gamma. So what I would like to do now? I would like to now compute the derivative of this map gamma. Okay, so I want to compute the derivative of this map gamma with respect to, say, a component xi I, one of these components. Okay, so I want to compute the derivative of gamma with respect to one of these components. And once I will calculate this, then I will see that under what conditions that derivative is 0. Okay, that derivative is 0, because that is going to give me what do you call the critical point of this map gamma. You can already observe about the map gamma because it is depending on what do you call an analytic function. Okay, and E, analytic function psi, we know that psi is analytic, and E is really, you know, this kind of an expression. Okay, so this gamma is analytic. So it's not difficult to see that this map gamma is analytic because it depends on what do you call the map psi, which is analytic. This is, this is simply what you call an equilibrium point. So this is not going to create any trouble. And E of this form is also what do you call analytic actually. So this map gamma is analytic. The only thing now I would like to find, in order to apply the Łojasiewicz-Simon inequality on this, I want to apply what do you call, I want to find its critical point actually. And the critical point is going to be the point where the gradient of this function is equal to 0. So let's calculate that gradient actually. Okay, let's calculate this gradient. Okay, gradient. Let me say that what I said actually. So indeed gamma is analytic. Okay, gamma is analytic, obviously in small neighborhood of origin in Rm, because that will push these xi's or this vector to go into the W2 of 0. Okay, so gamma is analytic, and hence the gamma would depend on the map psi, which is analytic, which will make gamma analytic actually. Okay, and moreover, if, okay, so before mentioning this, before computing the derivative of the map gamma, let me mention one more thing. I know about that n composition psi operated onto G is really the identity operator operated onto G. So if I compute the composition or the derivative, the Fresher derivative of this composition, that how does that Fresher derivative is going to be? That Fresher derivative of the composition, so now if you remember, the Fresher derivative of G composition F operated onto some A and operated onto say H, okay, is equal to D composition, okay, forget about this, D composition, the Fresher derivative of G evaluated at F of A, okay, the Fresher derivative of G evaluated at F of A composed with the Fresher derivative of F evaluated at A. Okay, Fresher derivative of F evaluated at A. So this is really the composition rule actually. Okay, So I can apply a similar result and I can get this, that the Fresher derivative of n operated onto what do you call n psi operated onto some g, you can write it as the Fresher derivative of n operated onto some v, which is the output of psi of g, composed with the Fresher derivative of psi, okay, operated onto g, and this composition is going to be identity, because the Fresher derivative of identity, which is a linear map, is also going to be identity actually. Okay? You can treat v to be the psi of g. Okay? So this is what this equation is going to give you, and this also tells you, because this operator is being operated onto this Fresher derivative, or it's being operated onto what you call v, so I can also treat, so you know, one can immediately observe actually that this Fresher derivative dn operated onto what do you call v is a linear map actually. Okay, it's a linear map from the domain of the psi of g, okay, which is the domain of the Fresher derivative of the psi of g, which is what do you call h, okay, because the domain of psi is from h and throws it in L2. So I can say that this Fresher derivative is really a linear map from h into L2, and similarly, because you have an opposite relation as well, true, so psi of n operated onto v gives you identity, so you can deduce also that the Fresher derivative of the g operated onto g is a linear map, okay, from L2 into h actually, and by h I mean h2 intersection h1 naught actually. Okay, so since this is operating onto this and giving you identity, so whatever the domain of this is going to be the domain of this, or the domain of this, the operator nv is going to be the part of the domain of this actually, and which is basically an h, and it spits out the values in L2. So this is going to be a linear map actually. So, and d psi of g is also a linear map. I'll use this fact at one place. Keeping in view this information and this definition, now let's calculate the derivative of what do you call the map gamma. So let's calculate the derivative of the gamma. So what would be the, say, the derivative of the gamma with respect to some component xi j? Okay? So you can say this derivative is going to be, first compute the derivative of E, then composed with what is the derivative, because you can treat it as that E composed with this map. Okay? So the derivative of E is going to be the derivative of the gamma is going to be the derivative of E composed with the derivative of what is inside E composed with the derivative of what is inside psi actually. Okay? And the Fresher derivative of this is going to be 0, so you don't have to worry about psi. So this derivative is going to be the Fresher derivative, okay? Fresher derivative of E, okay? Operated onto, you know, psi of sum that goes from I equal to 1 to n, xi I phi I plus psi, small psi, composed with the Fresher derivative of psi, okay, of I equal to 1 to m, xi I phi I times the Fresher derivative, which is basically going to be the partial derivative with respect to xi j of this sum. Okay, this is going to be the partial derivative of xi j of this sum I equal to 1 to m xi I phi I. Okay, this is what the recipe is. This represents the composition. So these are the compositions. Now, what would be this derivative? Okay, so these are the vectors. So if you want to compute the derivative of the sum, you need to compute the derivative of xi I with respect to the xi j. But this is going to be the delta ij, okay, canonical delta, which is going to be 1, I equal to j, and going to be 0 if I is not j. In other words, if these two indices are same, so it's going to be like partial xi j by partial xi j, so this is going to be 1. And if these indices are different, the derivative is 0. So if this derivative is delta ij, then what will remain in this term? All terms will cancel out except the term with the index j. Okay, the term with the index j. So in other words, if you take this inside, so this is going to be delta ij. Let me write it. This will become what you call delta ij,